Okay, so this example is going to use the one of the questions from a past NZQA paper, which is this one here from 2013, which was around the length of matches for this high performance player. I think it was a squash player. So I've put in the notes how to deal with grouped data. So you'll notice if you look at this actual question paper, which you should look at for more detail about the situation, is that it's actually presented, the data is presented as a histogram. So you actually don't know what the actual individual values are, but you have the bins and you have the proportions. So what I've done is used those to set up the intervals and proportions, using again a sample size of 200 because it says it's a large amount of data, and my program just generates the number of values using a uniform distribution between the interval that you've set. Okay. Anyway, don't worry about too much. Basically, my software is set up to work with individual values. It doesn't draw probability functions, so it's not doing area, density, histogram type stuff. It's just working with dot plots. Okay, so that's the situation there. We want to investigate this normal distribution model. In the question, it gives you the parameters of the model to use, which is cool. Alternatively, the kids could look at the data and they could estimate the mean and standard deviation and use that as well. I think that's kind of cool because it's helping to build ideas of being able to estimate those values. So if I was being one of my students in the past, I might say, 45 is the mean for some reason because it's got the highest stack of dots. And then I might do that thing where I look at, I don't know, what is it, the range, and divide it by 6. There's some sort of approximation to the standard deviation. So 40 divided by 6, I don't know, it's a little bit less than 7, I might go for 6, and generate some values. And again, what you'll see, like the previous videos, is that it will adjust the graph a little bit so that things match up. In this case here, might have slightly moved that. Yeah, just watch out for it. I don't know what did that. Anyway, it might have slightly moved some of the values out. So what you can do is you can adjust the axes at the bottom however you want. There we go. That captures everything now. Okay, so if I go back up here again, you know, on the face of it, it's probably looking like the mean I've put in is a little bit too high. But what would be good, I think, is to convince students of that. So if you were to generate multiple samples using this model with mean 45 and standard deviation 6, and then track that shape for it, you know, basically let it run enough time so they can kind of see what's going on. You can transfer it over while it's still animating, like that, if you wanted to. I just wanted to make it super clear that on the right-hand side is the modelling stuff, and the left-hand side is the real stuff, so that's why you have to physically transfer it over. But you can see probably even initially that those wouldn't be particularly good parameters to use for your model. The mean's probably something a little bit too high, and the standard deviation may be okay, but the mean's a little too high. We'll just stop there for a second. If I go back here and look at what the mean was for that sample, it's 42.1. So if I try jiggling that down to 42.1, I think what I've set up is you have to run another simulation to reset the animation tracked shape stuff. So let's generate that now. Oh, I should take that off there. Sorry. And build it up. I'll just show you a few other things while it's building up. So at the same time, you can show students the middle, what was it, 95%. And you can see it's fairly stable. It's because we're generating quite a large number of values each time. You can also show them the mean, and you can see that it's jumping around a little bit. I'm not doing this because I particularly want to track the mean. There's other really awesome visual inference tools that have been developed by Chris Wild that will do a much better job of tracking the mean, but it's more just, you know, it's kind of cool that you can see that. If I just stop that for a second and show you a couple of other things. So you can do things like, you know, according to this simulated data, you know, what proportion of values are 45 or above, where you can see that's, let's say, 60 out of 200, or, you know, what ones are between 40 and 50, and you get this, 44 out of 200. You can see there's some interesting stuff happening with rounding, because remember, this data itself is actually continuous. And this is a random version of it. So, yeah, that's kind of interesting. Anyway. Right, and you can do things like the percentile. So, for example, if you wanted to find the median, put in the 50th percentile, it'll tell you that it's 40. Okay. I haven't focused too much on those aspects, to be honest. So they probably could do with some tweaking and development. The main thing for me at the moment is to do with this tracked overfitted shape stuff. Okay, so yes, let's transfer that over, have a look, and we can see that's looking not too bad. We didn't quite get that tail going out there, but otherwise it's not looking too bad as a model. I think there was some discussion around whether a triangular distribution model, a triangular distribution might work as a model, so let's try that out. In this case here, we might go with this idea that the lowest value is 20 and the highest value is 65, and maybe that the mode is sort of 42.5. Just making this stuff up, and run that. And then you just need to watch out for how the axis gets changed. In this case here, we really should stick to the same range as our triangular model, so let's go down and change that to there. And then again, let's run that and see what happens. I prefer to run it on the side first and see what builds up, and then choose to transfer it over rather than doing it run on the same side at the same time. Because I really want to make it clear this is the modelling side here. So this data I'm generating is coming from this model. This shape I'm checking is coming from this model. This is all the theoretical stuff. So this is, you can see that it's going to build up that nice triangular shape, but it's also going to include this uncertainty you have with using this when you've only got 200 values that you've observed in terms of the fit of the model. So again, we can run it for as long as we want, build up some shape, and then we can transfer it over, and it's not looking particularly amazeballs. So our model should be going through the data, not above the data. In this case here, you can see it's pretty much sitting above those values, but it's kind of too low for those two particularly high values there. You might think, oh, that maybe is to do with the rounding and everything like that. I mean, you can play around with the rounding if you want to, so you could, for example, do it to nearest 1. What you can see here is that you don't get as clear a view of the shape, but you could do that. That's one of the reasons why I've got this whole rounding thing happening, particularly if we're dealing with continuous distributions like triangular and normal distribution.